Good morning. We are going to look at rotations today. This is our third way to do transformations. We've looked at translations, which are sliding, reflections, which is flipping, and now rotations, which will be turning. With rotations, you're going to have, by definition, a transformation that turns every point of a pre-image through a specified degree and a direction about a fixed point called the center of rotation. It will tell you how much to spin it and in which direction. The center of rotation will always be at the center of your shape or at an origin. In this video, we're going to look where the center of rotation is in the middle of your shape. So for our first example, we're going to look at a pentagon with a center of rotation at X, and we're going to try to find the image of E for a 72-degree rotation about X. Well, where did the 72 degrees come from? You know from previous lessons that an entire rotation will add up to 360 degrees. To find out how many degrees it can turn to end up back on top of itself, you take 360 divided by the number of points on the outside, or the vertices. So in this case, we have 1, 2, 3, 4, 5. So I'm going to divide 360 by 5. If you type that in the calculator or do it in your head, 360 divided by 5 will give you 72 degrees. So every time I spin my shape 72 degrees, it will end up looking identical to how it started. For this example A, we're going to try to do a rotation that is clockwise. So think about how the hands on a clock turn. We're going to go clockwise the same way I drew the red arrow. If we're going to start at E, clockwise would be dropping down and to the right. So if I take E and I want to go 72 degrees, I will move one space down, which will be pointing at the end, and this will be the new location after a degree of 72 rotation. Now this is the same example, which is sitting on your paper, except now instead of looking at going clockwise, I want to show you if it asks you to do a counterclockwise rotation. Instead of dropping to the right or spinning to the right, we're going to spin backwards to the left. So I'm going to start again with that E and do the same 72 degrees. So if I start with E, one rotation of 72 degrees will get you to where the point P is sitting. If I would spin the shape, E would sit directly over the point P. Now changing this just a little bit, we're going to switch from E to now point P, but I don't want to go 72 degrees, I want to get to 216. This is just doing 72 degrees repeatedly to get to your new location. If I take 72 plus 72 plus 72, it will add up to 216 degrees. So when I'm trying to go clockwise, I'm going to spin it 3 times to see what the image will end up at. So if I start at P, if I spin once, this would be 72, spin again at 72, and one last time would be another 72. So my point P would end up at T. T would be the new image of P. This is clockwise spinning. So again, let's look at it when I would be going counterclockwise. Start with P again. Knowing that it's 216, I'm going to have to do 3 different spins of 72 degrees. So 1, 2, 3. So the new image of point P after 216 degrees of a rotation will end up at point N. So let's switch the figures a little bit and see if we can still do this. And instead of taking the center of rotation for the complete shape, we're going to base the center of rotation about point F. So even though F looks like it's on the outside of your picture, we're going to treat F as the center. So this will be the center that we base everything off of. The 60 comes from the 360-degree rotation to make the full spin. But if you notice, instead of 5, we now have 1, 2, 3, 4, 5, 6. So if I divide by 6, I would see that 60 degrees would give me my rotational symmetry, where the shape would end up directly back to what the original appearance was. I want to take M, and I want to do a 60-degree rotation. So let's look at clockwise first. 60 degrees from here, around point F. So I'm going to take M, drop it 60 degrees, gives me my answer for clockwise, which I'm going to put as CW. My new answer would be point E. If I want to go counterclockwise from the same point M, 60 degrees would give me counterclockwise CCW, new image of A. With all this with rotation, you have to understand that in order for it to end up in a same location, you have to know some things about symmetry. So let's just recap what symmetry is. Symmetry is just an isometry which maps the figure onto itself. So again, all these spins make the picture look identical to how it started. A reflectional line of symmetry is one half of a figure like a mirror. So if you're thinking about your line of symmetry that we were talking about with reflections, it's what would split it in half and looks like a complete mirror image of itself. So if you were trying to find the lines of symmetry or reflectional line of symmetry, you have to think about where you could fold this in half or cut it in half and have identical pieces. The easiest place to start is to look for horizontal and vertical lines that would cut this shape in half. If I do the horizontal line through this hexagon, I could take the top, fold it over the bottom, and it would be completely symmetrical. I can also take a vertical line and fold the left to match directly over the right. If you notice that the vertical line cuts the side in half, so if I would go through and cut all the sides in half, even though they're diagonals, they're still some symmetry lines. Also, if you go back to the original horizontal line, it cut through the corners of our hexagon. So if I will draw my lines cutting through all the corners, these are also lines of symmetry. So if you're looking at this picture, this hexagon has a multitude of lines of symmetry. You could count 1, 2, 3, 4, 5, 6 lines of symmetry. This shape, however, doesn't have as many lines of symmetry. If I want to check the horizontal line of symmetry, could you fold the shape to match up from top to bottom? In this case, it would not work. So this is not a line of symmetry. So now I can check to see if the vertical line would work. This line does create symmetry both on the left and right, and this is the only line of symmetry that would work for this shape. Instead of having lines of symmetry, think back to that 360 degrees we were discussing earlier. You could say you can have rotational symmetry if the shape will map onto itself in exactly 180 degrees or less. So a shape that you would have to turn more than half a turn would not have rotational symmetry. So let's look at a couple of examples where you can see if this would have rotational symmetry or not. Let's plot a dot right in the center of our triangle. And remember that this would be 360 degrees if I would spin it all the way around. So I get my 360. Since it's a triangle, I have 1, 2, 3 vertices. So I'm going to divide it by 3 and get 120 degrees of rotation. If I would spin this triangle 120 degrees, it would end up looking identical to what it started. So you would have a rotational symmetry of 120 degrees. I could spin it another 120 degrees and it would still match up, but I'm not going to say that 240 is anything with rotational symmetry. 240 is larger than 180 and it can't happen. This triangle, however, if you notice, looks a little irregular. Some irregular shapes will have rotational symmetry while other ones do not. I cannot spin this shape anywhere between 0 to 180 degrees and have it ending up looking like the original. If I would take this shape and try to spin it 90 degrees, it's not going to match up to the original. If I do 180, half a turn, not the original. I can't go anywhere past that. 180 is my limit, but even if I keep spinning, it's not going to end up the same until I spin it a complete revolution. So this is said not to have rotational symmetry. I find it easiest is if you have a shape on a sheet of paper, just to try to turn your paper to see if you can get the shape to look like the original. So let's look at one more. Here's an odd shape. It's irregular, but if you would take the shape and spin it, here's half a revolution or half a full spin, and it ends up directly back over top of how it started. So this has rotational symmetry of 180 degrees. That is the maximum degree that I can use, but 180 degrees would allow the original shape to end up back onto its original form. Look at these pictures. You can go through and try to pick out which ones you think have rotational symmetry and which ones do not. I would use these as some practice before going to your packet and attempting the questions in your packet. It's on the back paper. There are 12 shapes that I want you to go through and figure out the rotational symmetry. At what degree could it work? There are 4 questions on your packet page that do not have rotational symmetry, and there are some that may have more than 1 degree. If you get stuck or need help at this point on rotational symmetry, pause the video, raise your hand, and ask for help. Good luck!